Section P3 summarizes the first two sections of this chapter to lead you out of elementary methods into the more advanced and eloquent methods. The purpose of this is to make your work cleaner, faster, and more accurate. In this section, we will focus on domain and range, function notation, function composition, and piecewise functions. As we have been working through this chapter, our goal has been to broaden your view of the functions you read. In the past, you were only concerned with limited instructions. For example, I might ask you to solve the function, or evaluate the function if x equals 2, or I might even just ask you to graph the function. These were simple, straightforward instructions with a clear and quick end in sight. However, to truly study a function, we want to think about all of our knowledge of the pieces of the function and how they relate to one another, encompassing behavior, shape, placement, critical points, and continuity. We've dealt with the first four in our list in detail throughout this chapter. Now we need to discuss continuity thoroughly. Continuity describes the domain of a function. If all x values from negative infinity to infinity are represented in the function, we say that the function is continuous. If, however, there are any values of x which are not represented in the function, this causes discontinuity of the function, or in other words, a place where the graph does not exist. These areas of discontinuity can be seen as asymptotes, holes, gaps, or jumps in the graph. They are caused by either limiting the domain ourselves due to issues in our data. For example, if we are studying a function over time, then we would eliminate all negative x values since negative time does not exist. That's us manipulating our domain and saying, no, we're not going to accept negative values. So we limited it. Or there may be an issue with the mathematical laws of the function. And it would be necessary for us to be aware of these issues within the domain of the function so that we could protect the domain and not let anything bad happen to our functions. Let's begin by reviewing the algebraic functions. The first, most important piece of information we need to know is that polynomials are our perfect functions. They are perfect 100% of the time. They're continuous for all values of x, which means all real numbers are accepted in the domain. Also, our range will also consist of all real numbers. Remember, algebra has two problem children. These are radicals with an even index, and then rational functions with variables in the denominator. Let's look at the radical first. We have to protect our range from imaginary results. Therefore, whatever is inside the radical must be greater than or equal to 0, and we must limit the domain accordingly. With the rational function, we must protect the denominator from equaling 0. We begin by always simplifying the fraction first. If any variable factors can cancel during the simplification process, we identify these values of x as holes in the graph. Next, we look at what is left. If we still have a variable expression in the denominator, then we must eliminate any possible values where the expression will equal 0. These values cause vertical asymptotes in the graph. It's where the function is undefined. Finally, after protecting our domain, we look at the relationship between the leading exponents in both the numerator and the denominator. In this case, we are not looking for undefined areas. We are looking to see if we have any horizontal or slant asymptotes. So don't forget your rules that we learned in pre-calculus. Take a look at them now. Next, let's refresh our memories with the transcendental functions. Any function that is not simple algebraic is transcendental. That includes trigonometric, exponential, and logarithmic functions. You'll remember that sine and cosine functions are continuous. Their domain is all real numbers, and their range is between -1 and 1. Tangent and cotangent, however, are created by fractional combinations of sine and cosine. Therefore, both of these have values of the domain which are undefined. And at that time, asymptotes will occur in their graphs. Their range is -infinity to infinity. Cosecant and secant have reciprocal relationships with sine and cosine, and therefore they have restrictions on their domain, because whenever sine or cosine are 0, their partner, cosecant and secant, will be undefined and have an asymptote at that point. In addition, in the range, because sine and cosine range between -1 and 1, those values are eliminated from the range of cosecant and secant in the reciprocal. So their range is -infinity to -1, but not including -1, and then the boundary of 1, but not including 1, to positive infinity. Exponential functions do not have domain restrictions. They accept all real numbers from negative infinity to infinity for their domain, although the nature of their behavior does restrict their range. An exponential in its purest form will have a range bounded at 0, but not including 0, to positive infinity. No negative answers, no 0 allowed in the range of an exponential. The inverse relationship between exponentials and logarithmic functions causes logarithms to have just the opposite result. Logarithms have a restricted domain. No negatives or zeros are allowed inside a log, so their domain is from 0, not including 0, to positive infinity. And then their range allows all values to be included in their range from negative infinity to infinity. Now, let's do an example using function notation. Remember the simple days when you were asked to find f of 2? You would plug 2 into the function in place of the x and simplify until you reached your answer. Although this function notation may look complicated, it's really no different than the simple process that we used to use with the value of 2. Now, be careful as you plug it in. Just make sure that you're following the pattern of your function and the pattern that you're given. F of x plus delta x minus f of x all over delta x, and delta x cannot equal 0. We want to FOIL and simplify our algebra, distribute our negative, and we notice that we get to have a few terms cancel out. We'll factor out a delta x, and the delta x's cancel. But don't forget, even though we canceled it, delta x still can never equal 0. When we finish, our answer will remain algebraic. Moving on to function composition. Function composition is another tool that we have to use a combination of functions together to create a new function that better meets the needs of our data. This process also mirrors the process of evaluating f of 2. However, in this instance, we are using an algebraic expression to replace the value of x in our function. Piecewise functions allow us to do many things. For example, I can use a piece of a function, piecewise function, to fix a discontinuity that exists in another function. Or sometimes when modeling data, you'll find that real-life information doesn't follow just one function. It may become more complex over time. By limiting the domains and combining two or more functions together, we can create a more accurate model for this data. Now it's your turn. Answer the questions on the Google form located beneath the video. Remember, they are due by 6:30 a.m. And if you have any trouble, make sure you email me at lovetodomath@gmail.com so that you don't lose credit. But also, remember that you have other class members to contact. Work together, help each other, because it will make all of you stronger. Remember, you have 2 days to do this portion of the assignment. It is your responsibility to ask questions during class or during tutoring if you are experiencing difficulty. Good luck, and I'll see you tomorrow.